Okay, so welcome everybody. This is the 17th edition of our LightOn AI Meetup. Of course, this last years now, we are doing this meetup in a virtual format in order for everybody to stay safe. Thank you for joining us today. We are having two great guests from the States. Daniel Adrian, who is with the Argonne National Laboratory, and Vivak, who is with the University of Wisconsin-Madison. And they're going to give us a quick overview of the recent advancements in randomized NLA, as well as a demonstration of library implementation, the Julia language. So we're ready to start. It's your show, as Igor likes.
Thank you so much for having us. We're really excited to tell you about our work, and this should be quick and informal. So please feel free to just stop us and chat with us whenever you need to ask a question. So again, we're going to be giving you a biased review of randomizing numerical linear algebra. So with a focus on randomized methods for solving arbitrary consistent linear systems, which is what we particularly work on, and we'll talk about why that's going to be. And then we're going to discuss our approach to building an RNLA library, specifically this one, rlinearalgebra.jl, and provide a short demo. So why are we interested in a library in particular, and why are we doing this work? So RNLA is a pretty quickly growing field. It's giving us the opportunity to overcome certain hardware limitations, to scale the number of linear systems that we can solve, or the size of linear systems that we can solve. And for that reason, it's become a bit of a jungle, right? There's a lot of methods, and it's unclear how to benchmark these things, or which ones work better, which ones work worse. So, our intention here was sort of to organize all these things and give you an overview of what's going on in the space. But, Martinson and Trope sort of beat us to it, and they have this really lovely document called Randomized Numerical Linear Algebra, Foundations and Algorithms. So what we're going to do is we're going to focus on something that's sort of missing from their overview, which is solving linear systems, in particular consistent linear systems. So here we have a linear system AX equals B. A is a November by December matrix, so N by D matrix. And typically we're going to assume that it's consistent, okay? And here's a bunch of references. So we have some work out in SciMax, we have some work under review in different places, but all of these deal with solving consistent linear systems, and we can get into it afterwards. Again, I want to keep my part of this brief so that way we can move on to the more interesting stuff with Daniel. Okay, so just to give you a sense of the scope of randomized linear system solvers, there's really two types. So the first type for arbitrary systems is row action solvers. So you're going to start off with some vectors, WK and Rn. Remember, n is the number of rows that we have in our matrix. That's the number of equations we have in our system. And we're going to do this type of an update. So we look at our residual B minus AXK. We take its inner product with this vector WK. And then we're going to move in the direction of A transpose WK. So this is a vector in the row space. And we add that to our XK to get our XK plus 1. Okay. Now you've seen this before. And typically this product between WK and A, or WK and the residual, is extremely inexpensive to compute, such as a Kaczmarz method, right? So typically we might just be selecting one row at a time, but all of that falls into this row action solver framework. The second type that we might think about is where we take our WKs and RD, and we do the following iteration. So we look at the residual of the normal equations, we multiply that by WK, so we take the inner product of WK, and then we move in the direction of WK to update or iterate XK. Now, again, these methods are only really useful when I can compute these things inexpensively. And so typically WK could be a coordinate selection method. So we select a column of A, and this gives you coordinate descent, or randomized coordinate descent. Okay, so these are two of the big types of solvers that you're going to see, two classes of solvers you're going to see for arbitrary linear systems. Now, there are some basic variations that you can think of very easily. The first one is, instead of doing vector value WK, like I showed you before, we can use matrix value WK. Simple enough, right? We can do matrix operations instead. The next thing that we can do is we can sample these WK, or we could choose these WK adaptively based on some finite amount of historical information. Okay, so think of max residual, which only looks at the most recent piece of information and then just chooses what equation to select next. We can choose a matrix value WK that adaptively is based on a finite amount of history. So again, combining adaptivity with block operations. And then the last thing that we can really do is we can leverage all historical information, and we can do so in a computationally efficient manner to orthogonalization. And it turns out that this is equivalent to sketching and solving, except we can pick the size of the sketching dimension generically. So I can grow that sketching matrix. If you're not familiar, don't worry about it too much, but what this lets us do is basically like a variation of QR that grows adaptively for randomized solvers. Okay, so here are some general thoughts, and then I will hand it over to Daniel. If you're going to use randomness, continuous random variables offer the best performance in terms of convergence. But as you all know, which is why what you all are doing is kind of exciting, is that traditional computing hardware makes this prohibitive, right? You can't really do this reasonably on traditional hardware. Block methods are provably better from a theoretical and computational perspective. You can see that block operations, higher level operations tend to be better. So if you could do block-based methods, always go in that direction. Adaptivity is a really important ingredient, right? If you want good solutions quickly, you can't just do arbitrary things. You want to make sure that you're sampling from the right parts of the matrix, or you're careful about how you're designing your WKs to make sure that you're taking advantage of whatever hardware you have, plus whatever mathematics you're trying to do, right, for your particular problem. And then the last thing is maybe something that, you know, maybe people don't think about too much, but it's when does randomization not work so great? When the information is well mixed across your coefficient matrix, randomization isn't going to improve anything, right? Because randomization is really just mixing information. And if it's already mixed, you're basically doing unnecessary calculations. So with that, I will hand it off to Daniel.
I didn't realize I was muted, sorry. Thank you, Vivak. So as Vivak mentioned at the beginning, there has been a recent explosion of interest in randomizing algebra, and a wealth of new methods have been developed, which makes it very difficult to track recent advances. And in particular, this is a difficult situation if you are a researcher working in this field, because if you develop a new algorithm, you want to compare the implementation of your algorithm against existing ones. But this can be very time consuming. And what happens is that people do not compare with the state of the art. And then we don't really have a good view of the field. What algorithm is better, in what situations, and so on. So, and of course, one of the reasons that these comparisons also need to be done ceteris paribus. So sometimes you might get some code from some web page that implements randomized whatever, and then you compare it with your implementation, but that doesn't really mean that your algorithm is going to be faster. It's just the implementation can change. And another reason or another motivation to create a software library is that we want a little bit more of accessibility from other fields. Randomizing algebra promises a lot, but we are not seeing those implementations that people can readily use, as in traditional numerical linear algebra or other fields. There are some specific computations like the randomized SVD or the randomized trace, which have been popular in AI type of libraries, but we haven't seen any comprehensive library that for randomized algebra. So we decided to leverage our work and then do something on it. Vivak, can you? Thank you. So what will be a good randomized algebra library? Well, for us, it should have these 4 features or these 4 properties. It should be accessible. That means easy to use, and that people that want to develop and go deep into the library should be able to do it. But people that just want to use it for their application, then also shouldn't be discouraged by the complexity of use. It should be extensible, and this is very important. So new algorithms should be able to be added without modifying all the code. There are some libraries that in numerical linear algebra that tend to be very monolithic, in the sense that there is not much code reuse, and that's fine for some specific numerical algebra computations, but for randomized linear algebra, I think it's not okay. Then another very important thing is that the library should be composable, and this is to allow building algorithms not in a monolithic way, but by composing and switching different kernels or blocks that represent fundamental operations in an algorithm. And it has to be inspired in very well established numerical linear algebra algorithms such as BLAS, LAPACK, and PETSE. So taking this in account, we have developed a prototype of how we would like a library to look like, and we are working on that. Try to make it effective. Can you? Thank you. When we started to develop this library, we chose the Julia language, and we both have experience with different languages. C, C++, Fortran, Python, but we are very excited about Julia for the numerical, for scientific computing. The reason is, one is focus on scientific computing. It has similar syntax to MATLAB, which it's good because there are many people that come from, like many students that come from numerical computing fields that do not really have experience going deep into the code, into the metal. So they don't have experience programming low-level languages. But at the same time, it has very nice high-performance capabilities, and it has very good interaction with MPI. It has a very good GPU interface. Everything is compiled with LLVM, so all of these things are very, very efficient. And the most interesting for us feature is the multiple dispatch, which if you come from a C++ environment, you might be familiar with this. But the idea is that we might have an algorithm that we implement that takes a matrix or something like a matrix and some vector, and we want to do some operation, for instance, a projection. And one very valid way to program this is in a very abstract way. So maybe you get a row and then you project that X into a row or whatever. And maybe you don't want to say anything, and that's fine. But maybe you want to specify that your P is a matrix, and then you might be able to leverage something from the computation. You might be able to say, well, it's a matrix, so it's going to be a chunk of memory that is in the stack versus other type of matrix that might be like some stream of data or whatever. Or we might find that we want to experiment with mixed precision computation, because we thought that maybe the matrix actually comes from like this randomized type of whatever. It doesn't matter if we are high precision. Let's put low precision and then keep the vector. So we can experiment with that. Or we might find that P, your matrix is a banded matrix and you want to exploit the structure. So in all of these cases, you can write your own function that is specialized, and then Julia will use multiple dispatch to dispatch the correct functional runtime. And it's very clean, looks very nice. And for randomized linear algebra, where matrices might be on the stack, they might be, or maybe they might be streaming operations. So we are sampling from something on the cloud. That is important. Next slide, please. For the design of the library, what we did is we did a lot of field work, and we tried to look for different all of the different methods that are out there, and then we realized that for instance, for a basic row projection method, you usually have a sampler and a projector, and then you can switch your sampler and you can switch your projector, and you will have a different method, completely different method. And the sampler sometimes is, for instance, you have the Kaczmarz weighted residual, and depending how you sample the columns, you may have a different method as well. So if you sample it, you can sample uniformly, you can sample on the sense of Stromer and Versinin. So all of this means that if we are able to capture these basic kernel operations, then we are able to allow users to exchange or experiment with this by interchanging these basic operations and obtain new methods or new stuff. Next slide, please. So the design of the library that we work on is modular. It inherits some design choices for PETSI. So we basically have a linear solver object, which we call RL solver, and a function rsolve. And this RL solver is, as we showed before, is a composition of a sampler and a routine. And the sample is how we're going to sample from the data matrix, and the routine is how we're going to project or what we're going to do with those samples. And then it has a logging mechanism and a stopping criterion, which actually that might be trivial for numerical linear algebra, but for randomized linear algebra, how do you log or how do you stop is not trivial, because you don't have, sometimes you don't have access to the whole matrix, to the operator. So you have to use different techniques to see where you are in your computation. And we always provide defaults. Like for instance, so the default RL solver is a row run cyclic sampling with row projection, and then this is the logger and the stopping criteria. Next slide, please. The idea is that the randomized linear solver, it holds convergence data and linear solver type, and then users can define new kernels for projection, cyclic, and they can exchange it, and they can play with it, and they can create new algorithms or test their implementation against other things. And then we leverage a common infrastructure. That means that we can do comparisons in equality of conditions. Next one. And then all of this is assembled in a generic rsolve interface, which takes solver type as an argument, and then some operator A and some matrix A and row column vector, and then an output solution. And one of the things here is that in this function rsolve, there is a lot of abstraction. So we don't really say anything about A and B because we don't want to. Because we want this to be as close to the math as possible. And then as we go deep, we start to talk about specific numerical optimization, or do we want to use some specific type of A or so on. And then if we want to implement new algorithms, there is no need to rewrite the code. Like yesterday, I was in a talk about mixed precision arithmetic in numerical linear algebra, and they were talking about rewriting a Fortran routine completely to just change the type to have precision. And this is not the case here. We can just change the precision of the operator and everything will work. Next slide, please. So we are, this is still an ongoing work, a very, very rough prototype. We continue, and we are continuing reading the literature and implementing algorithms. Right now, we are interested in trying to implement sample Choleski for graph Laplacians, randomized Gauss ideal, and other things that are lacking in our library. And we like to experiment with GPUs, GPU architectures, matrix methods, and of course, any sort of device that we can use that we can interface with the library. That would be cool. Next. Also, we have like many open questions. So for instance, doing automatic testing for correctness in this type of libraries is challenging because everything is randomized. And then one of Julia, for instance, they don't assure us that the implementation of the randomized of the random numbers is going to be consistent among different releases. So what they say is that relying on a specific seed to generate a stream of numbers during unit testing is discouraged. So is there any way to go around this? Because if we want to test the properties of the methods, that might be very time consuming. Next slide. And yeah, thank you. That's it. So the library, we have it in GitHub. I will share my screen. I will show you a little bit about the library, how it looks like. It's a very basic implementation. We just have the the general architecture, how we like to have it. Is not optimized at all, but we are playing around and seeing if indeed this library is extensible and if we are able to implement new algorithms without much pain. Okay, I think you have to stop sharing, and I was okay. So this is the GitHub page. If you are familiar with Julia, if you're not, the only thing that you have to do is you install Julia, and then you add this web page. And there's a little bit of tutorial here. And then we have some documentation here that talks basically about the library architecture, the documentation structure, and then we have a small manual here that explains the basics, how to create a linear system and how to do whatever. So if I take a terminal here, I don't know if you can. And if you can see this, I can just start Julia and then follow this manual. Call the library. Oops. Create a small matrix. Okay. So this is the basic functioning. There is nothing else. Like the first approach to the library is we wanted to make it very easy, no free. So sometimes you have like these C libraries that are, just doing the hello world is a pain. And then here there is some code. Where we, when we create the same system, but then we start to specify a solver type. So here we chose the random cyclic sampling, hyperplane projection, full logger, and so on. I can include this. And here the same. I'm just creating a new solver. I'm passing it with specific features, and then I'm plotting the residual history. RL solver. Sorry, RSolve. You can get by just going to the help function, you can get a little bit of documentation about its routine. So RSolver, what type of parameters does it take, and so on.
I think you missed an extra S in the RLS solver.
Oh.
So you see RL, capital R, capital L, capital S, and then so there you go.
Oh yeah, okay, yeah. Thank you. So yeah, this is like the main object that we have. An encapsulation for randomized and solver. It's a mutable structure, and then it has a sample routine, a sampler, a routine, a logger, and so on. And then we might have this deck. Yeah, the names look like incantations, like they're very low, but the thing is there are so many of them out there. If anybody has experience with randomized algebra, we really needed to to have something that makes it clear when you're typing it. So yeah, mutable structure with a field to store a cyclic order, and then some everything is very well documented and so on. And the idea is that if you're a user and you want to compare your algorithm, your new implementation of a projection or whatever with existing methods, you just go to, for instance, you want to do a new sampler, and then you will create your new sampler here. And so you go to, and you use the row deterministic and then the only thing that you have to say is put the name of your new sampler, which is going to be a struct. It is going to inherit of some abstract type, and then you specify your sample routine, which is going to take a predefined number of arguments, and it's going to do some operations. And by doing that, we provide like this common or uniform API for designing and creating new algorithms. And that's it. Thank you very much.
Thank you for this very interesting presentation and for showing us the ropes around your library. I think that we can start with questions if we have any for our two speakers.
Hello. Yes, I have one.
Yes.
What is the status of distributed computation or GPU computation on the library you present?
So we have not used it, but I have plenty of experience using GPU in Julia. It shouldn't be very difficult because in Julia, the difference is that you will, instead of calling an array, you will call it a Q array, and then everything will go through. The problem is that it's not optimized right now to use CUDA, but it will be very easy to go that way.
Okay, and for traditional parallel CPU computing, let's say, we
have not implemented any parallel stuff here.
Okay, thank you for your answer.
Sure.
So we have a question that we just got on the chat from Bill.
Yeah,
so,
sorry, I can ask it.
Okay, you can. Awesome. Yeah.
I just didn't know I'm a graph theorist, so I was curious about a bullet on one of the slides. You said you're working on Choleski decompositions for Laplacians of graphs. And I was just wondering if you had any insight or references into maybe what that would tell me about what the Choleski decomposition of a graph Laplacian tells me about the graph.
Yeah, maybe I can say something about that. So when you're doing a Choleski decomposition of a graph, what you're doing is you're sort of partitioning the graph into cliques and stars. Are you familiar with these ideas? So what it turns out to say is that the Choleski decomposition has a very clear interpretation for what it's doing. So when I eliminate, say, a node from my graph using the Choleski decomposition, I look at the star that it has, and I'm basically removing that node, and I'm creating a clique with all the things that it connected to in its star. And that is what a Choleski decomposition is actually doing when I'm operating it on a graph Laplacian. And so it has this really, really nice interpretation. And so what people have done is they've said, okay, well, when I do this sort of Choleski decomposition, the reason it starts becoming dense is because I start connecting all the elements in the star to the node that I've just removed using my Choleski decomposition, right? And that's where that density comes in. So what the randomized people have come along and said was, okay, well, we don't want that fill-in to occur when we're doing a graph like this Choleski decomposition on a graph Laplacian. So how can we avoid it? What we're going to do is, instead of filling in the entire clique, we're going to actually just randomly sample some of the connections. So we have a way of controlling the amount of fill-in that goes into it. And that is basically the idea behind randomized Choleski decomposition and what a Choleski decomposition is doing on a graph when we apply it to a graph Laplacian. I know that sort of veered away from your question, but the randomization part is somewhat interesting. So I just wanted to mention it.
No, that was great. Thank you.
Of course.
Good.
I've got
Igor?
another question. You were saying that you were doing this library mostly for people to essentially play with it so that they would essentially be able to handle different schemes and put them together and everything. There is another part of the equation where, you know, what you have in linear algebra from the very beginning are those specification benchmark, those spec bench out of which people can figure out if certain methods are doing better than others. And so I realized that it's not really what the library is for, but it's essentially yielding this. But isn't there another part of this where there is an evaluation that is kind of common for everyone to becoming, so that eventually the goal of the library is essentially getting people to have a better understanding of what methods are working better than others?
So this is a very good question, and indeed we are not focused on comparing ours with other, you know, I don't know if you mean like LAPAC or other type of you know, benchmark, like common benchmark.
No, it's more like I mean, my sense here is that I see many different randomized techniques that are even competing with each other.
Yes.
And as a hardware manufacturer doing those randomized type of things, we're kind of trying to figure out exactly where the space is with regard to what we do in terms of operations and everything. And so it's a little bit like what you were saying, that there does not seem to be a factor by which we can evaluate whether or not such and such techniques are doing great or not great. And so there is still, as you said, the jungle part of it. It's the Wild West, in the sense that everybody's pushing for their randomized type of techniques, but we don't really know why it works, why it doesn't work. There is not much known things about the data in the first place, so we don't really know what generalize and so forth. So my point is not really to compare it to exact methods, somehow exact to numerical precision type of things, but it's more along the lines of out of the many different techniques that are part of that zoo, is there a way for the community somehow to come up with specification benchmarks that allow people to figure out exactly, oh, there are things that are working better than others?
Yeah, that is something that we like to do. I was cautious at the beginning when you asked that question, because there's another group, which you might know the people, James Demel and Nogara. They are doing an implementation that is supposed to be competitive and interface with LAPAC, and is very biased towards high performance computing, everything implemented in C++, and they are moving in that direction to see are randomized algorithms capable of competing with state-of-the-art whatever. We are more concerned about sorting out the jungle in randomized algorithms and creating those benchmarks. And in particular, one of the main issues that we have is that many of the randomized algorithms, they are not meant to be used with data that is in cache. In the heap. They are meant to be used for matrices that cannot fit memory. And we don't really have anything that can, but that we can use numerical linear algebra with this type of matrices. So for instance, with something stored in the cloud, something that comes from sensors, or things like that, we don't really have anything. So we are, because we are only two people and we are limited, we are just focusing on this specific jungle problem and try to find ways to create those benchmarks. But it's an ongoing effort.
And just taking a step back, this is something that I think about a lot more. And so this is why Daniel and I think work so well together. We've liked working so well together for so long. Is that the question that I would have is, if you have a randomized method, how do you make a comparison, right? And fundamentally, so my background's in statistics. You know, we've done a few things in our work. One thing that we've done is we've said, okay, well, what are the key properties that an arbitrary method needs to satisfy in order for us to show that it converges exponentially fast to a solution? Okay, so we did that. We have the mathematics down. We said, the last 80 years, here are all these methods. It all fits in within our framework. We can prove convergence. Okay, so everything converges in the worst case exponentially fast. So basically anything you could think of is going to work. All right, well, then we have this question of how do we know? So how do we know, and then how to compare these things in real life? How do we, and so to me, this is a hypothesis test. So statistical hypothesis test. I ask the question, is this better than this? And somehow I have to estimate that. And so when we're doing testing and we can't set the seed, this is how we have to do it, right? We have to actually generate data and ask this question. Here are these two methods on the same benchmark. Let's call it, suppose we even were able to identify what those should be. How do we then do that comparison even? So this is some idea that we're still trying to play out and sort of develop a little bit more rigorously, because, you know, we need to be able to tell you, like, well, what's your false positive rate? What's your false negative rate? Like, how can you, so now I can't definitively say that something is better than something else. I can say up to some probability, I know it's better. Up to some high probability, I know that it's better. And that is the thing that we're sort of building out. There's when you have this loss of determinism, you have to think very carefully about what it means to compare to a benchmark or two different algorithms. Yeah.
Okay, thanks. One more thing, I was, when you're talking about those matrices, those A matrices, they have n rows and d columns. In the cases you're looking at them, I'm looking at the fact that you're looking at Kaczmarz type of algorithm, so I'm kind of thinking that you have more rows than columns, right?
So n and d can be arbitrary. In fact, with the theory that we've developed, it could even be streaming. So it doesn't make a difference. And you could also have column methods. So like I can look at generalizations of Gauss-Seidel, so generalizations of coordinate descent. So I can hit my matrix from the right-hand side with a random projection, right? So if you gave me somehow a random linear combination of the columns, and so you generate another matrix, we can also do stuff with that, and the theory still applies. So we can still say, even in that case, that we're going to have exponentially fast convergence, and we can then say, when I implement this algorithm, I know that in the limit it's going to work. I know that it's going to converge at a certain rate. I might not be able to calculate that rate, but I know that's going to converge exponentially fast. And then it all comes, even in the worst case, and then it all comes down to how do we now compare these things realistically, right? Just like your first point was.
Yeah. Okay. And I'm coming from a different world somehow. At some point in time, you realize that when you're looking at underdetermined systems, you basically have an infinity of solutions somehow. And even though the L2 solution is kind of the one that everybody kind of likes by default, because it goes it's an easy solution, quote unquote. Are there any push in directions where you're essentially asking those solutions to be optimized for certain properties like sparsity or low ranks, and I mean, it opens a new kind of worm in terms of using these randomized techniques on top of those new conditions. Have you had any experience with that? I mean, I know it's difficult to even look at just the randomization on itself, but has there been work recently on essentially looking at those randomized methods with the added constraints of positivity, low rank, and so forth, that you find in the normal literature, let's say?
Yeah, so historically, this has been a very common topic for in machine learning, right? So stochastic gradient descent can easily be applied to solving a linear regression problem with the sparsity L1 penalty, right? And you can, it's a randomized method and it works fine. It's a generalization of Kaczmarz. So that's been there. If you want to impose positivity, you could do the same exact thing. You just do a projection after every iteration. And so that's been there for some time. There's no issue there. The challenge there is that you then lose exponential convergence, right? I immediately lose that because no longer are all of my equations solve exactly the same problem. Whereas when you have a consistent linear system, you have exponential rates of convergence. So there's sort of and just to, so like, yes, the L2 solution, everybody really loves it, right? Everybody's really into the L2 solution, except when you start going towards large scale problems like data assimilation, right? There, I have an overdetermined system every so often, but I have prior information. And so like, if I just initialize that my piece of information and I let it solve, I'll get a closest solution, but I don't need to worry about some sort of L2 penalty. And there's ways of integrating penalty functions into the system. So for example, if you want to do an L2 penalty, an equivalent thing that I can do is I can actually just add noise to my rows of my matrix. Because then when I look at the expected value of the residual squared, it actually turns out that it's my original problem plus a penalty on the L2 term. So on the solution. So there are many ways of integrating into these ideas, but for the types of problems that you mentioned, it's all been in terms of SGD.
Okay. Cool. Thank you.
Thank you for the questions.
Thank you. Do we have any last questions for our speakers? If not, I have one last question. Since you know most probably that at LightOn we are talking with at the same time with people into the scientific computing, but with people in the machine learning world at the same time. We ourselves were thinking about having our own libraries in Julia, the libraries that we use for our OPUs, for optical processing units, and all that, but it's a work in progress. We haven't done that yet. So I was wondering potentially if you were thinking of releasing your library in any other language, more, I don't know, less exotic for the people that are not dealing every day with scientific computing aspects.
I mean, we like to, but I think that we don't really have enough manpower to do it.
Yeah,
we're only 2 persons right now, and yeah. But
yes, of course, understandable.
I encourage you to. I come from a Python and C world, but I encourage you to try Julia if you have time, because there is a lot of new computational things coming in that area, and at least in the US is really becoming a very fastly adopted. But it's true that you have a community in Python that does data science, and they are with TensorFlow and Keras and all of that. And then you have Julia people that are doing more optimization. And so, yeah, I understand that there is this.
There's this gap, but yeah, it doesn't need to be there.
Yeah, but I don't know, like that you have a Python wrapper, I think, of your API for LightOn.
Yes.
But I guess that the inner stuff is done in C, or is done in some sort of low-level language.
Yes.
It should be easy to wrap that in Julia.
Julia plays really well with C, like very well with C. So it's not so, even if you go to R plays super well with C as well. In fact, like 37% of like the code base or something is entirely in C. It's just an interface with R. And the other plug that I have for Julia, which Adrian, which Daniel called me on a very long time ago, when I first started using it, he's like, the only reason you're using it is because you could use Greek letters. And I said, yes, absolutely. That's the only reason I started using Julia. So it does make things kind of nice in that way. Yeah.
I had another question that was a bit more broad, let's say. I see, Vivak, that you were over at this randomized, you were in this randomized report that came out from the DOE a while back, which was really the minds of all of you guys on the state side on what those methods could essentially bring to scientific discovery and so forth. And so my question to you is, I mean, at LightOn, we've been believing in those randomized methods for a long time right now, because, I mean, essentially we built some hardware around it. Do you get a sense that somehow it's being taken seriously, or are we still in the realm of it's nice, but we'd rather have 16 floats accuracy from those sensors, and so we're going to be putting more money into sensors than just trying to have large experiments with smaller sensors, but now trying to get a sense of what's going on. What's your sense on essentially going to that meeting with those 2 days, talking about scientific discoveries in the many different type of areas? And how do you come out of it thinking that those techniques have a future, or is it going to be staying like for those people that are really having very large models and trying to slim them down?
It's a great question. So one, does it have a future in the US? Definitely, because those meetings tend to precede a request to the Congress of the United States for money. And so there's definitely an interest in funding these types of research activities. So I do think that there is, at least in the next 10 years, a pretty good future for these types of methods. And if they prove themselves, they'll continue to be one. And the other things that the one big thing that I took away, and we sort of talked about this earlier, was that people that want to use these libraries, they have two really big hesitations. One, they don't necessarily have access to these things, which is what we were trying to solve to some extent with this Julia library. And so that they could play around and sort of adapt these solvers to their particular problem, because they want to play around. And the second thing that I took away, especially from a lot of the practitioners that were there, they're doing these sorts of large scale calculations that could benefit from something like this, is that they don't know how to cope with the loss of determinism. So they don't know what to do. And coming from a statistics background, I had a hard time understanding this idea, right? Like, I'm like, what do you mean? Like, everything's random all the time. But it's a really interesting thing in that they're really hesitant because of this. And so this brings us back to this other question of comparisons. Like, now, how can I go ahead and tell you that this is doing what we want it to do, at least with a certain degree of probability, right? That you're going to get the answer that you want with some degree of probability. And especially if you start to interface this into a larger calculation, right? Because they're interested in doing this not just once, but they're solving 1,000 linear systems in a single go. And so now they have this accumulation, false positive, like what's going on, right? So we need to be able to also answer this question of, how do I comfort you to, when you get your final answer, I'm telling you with probably 95%, this is a really good answer. It's done what you want it to do. So you say, and so then you're weighing time expectation, right? Like, okay, if I did this deterministically, it would take me 100 years. If I do it this randomly, it takes me 5 years or whatever, or 5 minutes, and with 95% chance I got it right. Okay, that's a pretty good, in expectation, you've saved yourself a lot of time. And so, how do we sort of build these tools out alongside of the guarantees that we need to provide, so that way and not just like mathematical guarantees, those are kind of useless for them. They want computational tools that they can use to say, yeah, this is giving me the right answer. How do we provide both of those things to make sure that people, when they interface it into their applications, they're happy with it? So those are sort of the big challenges that I really took away from that meeting to making this successful. Okay.
And so, I mean, besides the funding horizon that the DOE seem to be opening up for, do you believe that there are cases by which it's not a question of if, it's a question of when some of these techniques have to be used, because there is a compute wall that we just cannot cross? I mean, we see that at LightOn on large language models like GPT-3 and so forth. And so I'm kind of wondering if we see the same compute wall on other type of things that you guys have seen at this meeting, or is there a sense that, oh, we're just going to get a better supercomputer type thing?
I have an answer, and I think Daniel might have an answer as well to that. So I'll go with mine first, and then Daniel, if you have some thoughts on these things, I think you certainly do. So there's this professor, I think he's at Princeton, Wynan E, who talks a little bit about this, and he's quite senior, and he's thought about this for a long time. And his answer is basically, you have no choice, in the sense that you're going to have to start using these things if you want to do things that go across multiple scales, right? Because to some extent, the lower scales, I don't need high accuracy, and the larger scales depend on the lower scales being reasonable. So randomization is a very nice bridge within the scales and across the scales. So his sort of thought was, yeah, you have no choice. And he's a very careful thinker, so I think he might be right. But again, that's me speculating. I don't personally know. I given the examples that he gave, I believe that he made a very compelling argument for this.
Yeah,
Thank you.
I might add a couple of some thoughts. As you know, like a lot of the advances in machine learning and AI have been propelled by advances in computational architecture, and in particular on GPUs. And then one of the things that we are dealing with right now is that all of those advances in computational architecture are stopping. We don't really have better CPUs. CPUs are becoming very, very hard to make it smaller and faster. Energy consumption is a big issue. And then GPUs, the same thing, is becoming hard to get better GPUs. They're expensive and so on. So we really need completely different. If we want all the AI machine learning revolution to happen, and we need different type of computing model. And that's what most DOE people and everything, everybody's working on that right now. So it's an open question, but we have funding, and I think that this is going to be an important potential answer to that problem, randomized algorithms.
Okay, randomize all the things, like we say at LightOn. Thank you.
It's already randomized, and there's no value, right? That's the only thing we have to be careful about. Yeah.
I see the academic coming back.
Great. So if there's no further questions, we have already spent like an hour. It was a very interesting discussion, at least for me, and I hope for all of you. So I would like to thank you again, Vivak and Daniel, for your nice presentation. And we would be happy to continue discussing in any way or form about these things that are of interest for you and for us. So thank you again
very much for having us. And if you end up making an interface for Julia, we'd be happy to try it out for us too. So good luck with the product, and thank you for having us.
Thanks a lot.
Thank you.
Okay.
Thank you.
Bye-bye.
Thank you very much. Bye-bye.
Thank you.
Bye.